Hello, my name is Gabrielle Taylor. I'm going to be doing homework 2, part A. So the first one is we are going to use the van der Waals equation to solve for both coefficients of A and B. So the van der Waals equation for state is going to be P equals RT over V minus B minus A over B squared. Okay, so this is van der Waals equation. So we want to derive this at the critical point. So let me draw a graph for you real quick. So this is a pressure versus volume graph. So when the temperature equals the temperature at critical pressure, there is an inflection point right here on the graph when temperature equals a temperature at critical point. And then this is kind of it at like the temperature is less than the temperature at critical pressure, and this is kind of it as the temperature is greater than temperature at critical pressure. Okay, so this is the inflection point. This is what we need to know. Okay. So what we know about an inflection point is that its derivative of its first and second is going to be 0. So this is going to help us cancel out some things. So let's take the derivative of this at the critical point, and we want to evaluate these derivatives at the critical point so that we can solve for A and B. So our first is going to be dP over dV equals, and these are going to be with respect to volume. So we want RT over 2 minus B. This is squared, and that is negative for the derivative. And then we have A over B to the third, and that will be negative and plus 2. At 2 at the top, so 2A over B to the third. And then for our second derivative, let's take the derivative of V, so 2R and then RT, and then that one brings a 2 to the top. I'm going to move this over so we can get the negative. So this should be negative. It should be 2RT over V minus B to the third. And then on this side, that would be positive actually because that cancels out with that negative. And then this would be negative. This would be 6 and B to the fourth. Okay. And now we want to evaluate these at the critical the critical point. So CP over CP. And now we need the temperature at CP. C. So the temperature and the volume are going to be both at critical. So what did we find? That the inflection point, and we know that at the inflection point, the first and second derivative are going to be equal to 0, and that is at the critical point. So since we put the T, we put our temperature and volume both at the critical point, that means we can make these equal to 0. So these equal to 0. Now let's make these by itself, since it's on that. So this one's going to be 2VC to the third equals RTC over VC minus B squared. And then we have 2RTC over VC minus B to the third equals 6A over VC to the fourth. Okay. So we put everything off to the side and made it equal each other. So now what we want to do to cancel these out is to flip these to do the inverse. And let's just do the inverse of the bottom one. So let's do the inverse of this. And then when we multiply by it, we should get a lot of cancellations out of it. Okay. Okay, so now if we multiply this to this, let's see what we get. So the first thing is RTC is going to cancel out, so you're going to get 1. You're going to get 2 at the bottom. This is just going to be VC minus B. This is 2. Okay. Next, you have BC, 2A. So the A's cancel out, so you just get 1 over 3. 1 over 3, and then you have a VC at the top. So this is just VC over 3. Okay. This is pretty good. So what we found is we just had our equation and we pretty much canceled out A. So now let's find B, since we can get this pretty much solved without B. So let's cancel out, let's put 2 over, and then let's subtract. So we have VC minus B equals 2 over 3 VC. We're going to subtract that. That's going to become negative 1/3, and then we're going to move that negative over. So this is going to be VC over 3. So this is our B coefficient. Now, we're going to substitute this B back into our first derivative here to find our A. So let's put it as RTC over to B. So this is going to be BC minus BC over 3 squared. And then this is going to equal 2A over VC to the 3rd. Okay. All the B's are put in, so this one's going to be, so let's simplify this. So this is 2/3 VC over squared. And this is 2A over VC to the 3rd. Okay, so this is going to be 4 and 9, and then you flip it, so the 9 goes on top. So let's go over here. So it's going to be 9 RTC over 4. And then you have a V squared at the bottom. V squared at the bottom, and then you have 2A over VC to the 3rd. Okay. So now we just solve for our A. Okay. So we're going to bring that to the top. So we're going to have 9 over 4 RTC VC. Yep. And then 2 over A. And then that makes this 2/8 over RTC VC over A. Okay. Let me just check this real quick. Okay. Cool. So we have our A. So we have our B here and our A here. So what we want to do is we want to figure out, we want to put these back into here so we don't have A and B anymore. So we put these back in our van der Waals equation for state. So let's erase some of this. So let's put it back in here. So we have P, RT, V. These are all going to be at, this is all going to be at the critical point. So B minus VC over 3rd minus A over, A can be substituted as 1/8 over R TC VC. And then this is VC squared. Okay, so let's get some cancellations out here. So this can be crossed out, this can be crossed out. And then this could be 2 over 3 VC. So P equals RTC over 2/3. The 3 comes up to the top, 2 stays at the bottom, VC. And then we have minus 9 RTC over 8 VC. Okay. So we have some common things. RTC over V, RTC over V. So let's take that out. So we have P equals RTC over VC. And then this is going to be 3 over 2 minus 9 over 8. Okay. And now let's multiply by 4 on this side. Common denominator, that's 12. So P is going to equal RTC over VC. It's going to equal 3 over 8. Okay. So we got our answer as 3 over 8. It's pretty much this. And so why this is unique is because our ideal gas situation is going to say PV over RT is going to equal 1. And this is for every compound. Every compound of an ideal gas of PV of nRT is going to be at the same ratio. It doesn't matter the pressure, volume, R and T are all going to be equal. So why this is interesting is because it's saying that the ratio of P, T, and V at the critical point is going to be 3 over 8, which is different from the ideal gas of 1. So this is a really big thing that Van der Waals found out. So, yes. So the ratio is 3 over 8 at the critical point. And since we found A and B, you can use these for later equations for any kind of temperature you have, even for the smaller temperatures and smaller pressures, because the critical point is at when all phases seem to be meshed in between the vapor and the liquid phase. They seem to be indistinguishable. So now you can use them at smaller times, which is important. So thank you. Okay, so I am doing homework 2, and I'm doing part A3. So it says to generate PV diagrams for water over a temperature range of 275 to 900 kelvins in 25 Kelvin increments. And we're going to use the Van der Waals equation of state. Okay, so we have our coding right here. So the first thing we want to do is we're going to want to import NumPy as MP. And now, since we want to generate diagrams, we're going to want to import our graphs. So let's say from So now we have our imports. So the next thing we want to do is let's look at our cubic equation of state. So we want to make sure we find our pressure, volume, and temperature from here, right? So let's make our variables that we know. So let's put in our R, 0.34. Okay, and since in our last thing when we derived A and B, and we found that the critical point is the 3/8, right? We know that we've evaluated this at the critical point. So, and we're doing this at the water, so we have to put in our temperature and our pressure at the critical point. So our temperature is going to be 607. 86, and this is going to be in Kelvin. And then our pressure e to the 6th. Okay. And this is pascals. Okay. And now what we need is just our W, which is going to be 348. Okay. So we have our R constant, our temperature at the critical point, and pressure at the critical point, and we have W. Okay. So that should be good. The next thing we want to do is we are going to find our van der Waals equation. This is not going to be important to graphing it, but it's just going to show you how we're going to graph our cubic function. So let's define our van der Waals equation. This is going to be dependent on volume and temperature. So the first thing we want to do is let's go back over to here. It will tell us what our sigma and our epsilon are. So sigma is going to equal 0. Our epsilon is going to equal 0. Okay. And then like we derived for our van der Waals equation, that it's B is going to be 1/8 times R. I need to put a sign right there, times R times BC divided by BC. Okay, then our A is going to be, like we derived in our equation, 27 over 40, 64. And we're going to multiply this. It's going to be R squared times the temperature at the critical point squared divided by PC. Now, so after we know our sigma, our epsilon, our A and our B, now we're just going to return our cubic equation of state. Return, and it's going to just be R, and then we just went T, because we wanted a temperature at multiple temperatures of pressures. We don't want it at the critical point. So then V minus B minus A Okay, so this should be our cubic equation of state. This should be our van der Waals equation of state. So next, so after we found this, let's pretty much do the same thing we did for the cubic equation of state, which is going to be our SRK equation. So for our SRK equation, first we want to define our variables, and then after we define our variables, let's unpack that and let's put that into our cubic equation of state. So first thing we want to do is let's define, let's say calculate variables, and this is going to be dependent on temperature. Okay, so the first thing for our SRK equation is let's do sigma equals 1, epsilon equals 0. Okay, so we know our sigma or epsilon, and then we have our alpha. Our alpha has temperature reduced in it. So right here it says it's temperature reduced. Temperature reduced is going to be temperature reduced equals temperature divided by temperature at critical point. Okay, so after we have that, now let's calculate our alpha. So 1 plus Okay, so that's squared. And then we want to multiply this by 1 minus temperature reduced. And we want to do that by 0.5. And then all of this should be squared. Okay, this is good. And then after we found our alpha, let's plug this back in for A because we have it there. We also do need psi and omega before we do that. So let's do omega first. So omega is going to be 0.08664, and then psi equals 0.42748. Okay, so our A is going to equal psi times our alpha times our r squared times our temperature at the critical point squared divided by pressure at the critical point. Okay. Then B is just going to be our omega times R times temperature at the critical point divided by pressure at the critical point. Okay, let's make sure our equations are right. They are. Oh, okay, so they are. Now let's return. So what we want to return is our variables that we're going to need for our cubic equation of state. So we're going to need B, A, epsilon, sigma. So let's do A, let's do B, let's do sigma, let's do epsilon. Okay. So now that we have A, B, sigma, and epsilon, let's put it into our cubic equation of state. So let's define, say, cubic. Okay, and this is going to be dependent on volume and temperature. And now what we want to do is we want to unpack what we just found. Okay. Next, what we want to do after that. So after we unpack it, let's just return. And when we return it, let's just put it back into the equation of the cubic equation. So what I just calculated here, let's just copy and paste it for the van der Waals equation. It will be the same. We still want it as temperature and volume that are not the critical point. Okay, so after we found our critical point, this is going to be on our graph. This is going to be our y. So we have our graph that's going like this. So what we need to figure out is our x, and our x is going to be our volume. So our volume, figure out our volume. So our cubic equation is in log. So we need our x, or our volume, to be in log as well. So let's do MP log space. Okay, so we're going to do a start and kind of stop. So where are we starting at? Where are we stopping at? And how many increments we're doing in it. Okay, so where are we going to start at? We want to start really close to B, right? So do MP log base 10 of 1.0. It's pretty close to B, just above B. And since we have B in here, we have to go back up here. And let's put a B in here. And this is going to be B for our van der Waals equation. So V times R times TC divided by PC. Okay, so after we do that, we have our b in there. And now we need to do where we want to stop at. Let's stop at -2 because it should be close around there. And let's do increments of 1,000. Okay, let's see if this works. It does. Okay, so what we want to do first is let's just make our figure. So our figure equals make underscore subplots. Okay. Now, our question says that we wanted our temperature range from 275 to 900 kelvs and with an increment 25. So what we're going to want to do is we want to have a for loop. So for p in. So for the temperatures, we want to do an MP arrange. And so MP arrange says that we want to start, where we're going to start at 275, where we're going to stop at 900, and what we want our increments to be is 25. And then I think we do that. So now we have our for loop. So what we want to do for the for loop, so for every temperature, we want to add a point. So let's add scatter plot. So figure add underscore scatter. So our x, like we just calculated, is going to be our v, and then our y is going to equal our cubic equation, and then we have our v to t. Okay, and then what we want our mode to be, so we want this to equal lines. Okay, and then since we're gonna have multiple lines, let's just name each line. So name, so F, and then we want it to be our temperature. So let's just go by our temperature of what it's at. And then it's just gonna be in Kelvin, so okay. Okay, so after we have this, let's think about what we did. So we need to know what we're gonna need to update on our graph. So our V, we put V in a log because our graph is going to be log. So that means we have to update our x-axis to be log. So let's first do figure, update x-axis. So what we're going to want to do is type log. So now our x-axis is going to be in log. So after that, let's just make our graph is going to need to be bigger because we're going to 900, 275. So let's update our y-axis. So figure and let's say range. So what we want our range to be, just do from negative to positive. E to the 6 and so, and now we want 1 e to the 8th. Okay, so that's our range. So now we have a range and let's update our window space pretty much. So let's do fig update. Let's do layout. So we're updating our layout and we want it to be, let's do width equals 800, our height equals 600. Okay, let's see what we're doing with this. Okay, so after we put our layout on here, which is with 80 and 60, this is going to be our graph. And so our critical temperature and pressure should be around here somewhere, around here. Okay, and so this is the end of the code. Thank you so much.